So let me see if I get the, I don't even know if I'm connected. Yeah, it's connecting now. If it works, so I don't know if it's going to work or not. Yeah, you can still be engaged. I just want you to be aware that it is picking up the audio. I might need to install a VPN. Maybe it's not working. Cause it might not work because we're in here. I'm trying to think, how can I get a VPN on here? What was the thing called? BetterNet. I'm gonna try something, see if this works. Nope. I'm gonna open up the App Store. Nothing. Okay, so I don't think it's connecting, but I think it is recording. So what's gonna happen is, so ladies and gentlemen, we gotta monitor the volume today. So what we're gonna do, I'm under the impression that it is recording, and we're gonna do the lecture like normal. I don't think it's gonna go live just because of the Wi-Fi connections here or the settings, and I don't have a VPN installed right now, so I can't go live. But I think it is recording, and I'll just load it up later, right? So it's still gonna pick up all the audio, and I'm gonna let that kind of be. Okay. So what we're doing today, let's go here. Actually, yeah, we need to switch that over to this one is fine. Okay. Let's do screen capture. I think that's how it's gonna look. I'm gonna let that be like that, put that there. Okay, and actually one other thing. A little bit trippy. Okay, I think that'll do. Hopefully this works. So again, we won't really be able to see it until a little bit later when I load it. All right, and we're gonna leave that like that. And for us, we're gonna go here, just like that. Okay, so we're just gonna let it be. So keep in mind that it should be recording the audio. Let me check one other thing. Hello, yeah, okay. So this is, we're gonna continue our lecture. So we have let's do a quick discussion on the time. Let me see, I have a calendar here. So today is the 18th, right? Our last day, we're going to take the final on October 1st. That's our last day of class for this quarter. We're going to take exam 3 next Wednesday. We have today's lecture. We have Friday's lecture. By Friday, I just want to get to 5-1, and I think that'll be the last of it. So our goal is to do 4-2, 4-3, 5-1. If we can do 2 sections today, we'll be on target. We are recording this. It's not live, but we are recording it, so we should be able to load this to YouTube later. I'll just kind of be aware of that. Over the weekend, same kind of deal, like I do all my other exams. Okay, be on the lookout for a study guide. That takes top priority. You know, that's not a guarantee, but there's a high probability. You want to start there if you don't start anywhere else. So whenever you see my study guide, you want to focus on that. If you're comfortable with everything there, you should be okay. Beyond the study guide, you want to go through the homework that's been assigned. Another thing is that in preparation for the final, to prepare for my final, what we want to do is take the old exams. That takes top priority. So exams 1, 2, and 3. Top priority of those, you want to be comfortable with every question on those exams first. Once you're comfortable with those questions, then we're going to move on to the old study guides. But don't go to the old study guides until you're comfortable with every question on the old exams, right? So you want to get them corrected, team up, ask questions, things of this nature. So exam 3 is next Wednesday, and then that Friday, the 27th, we'll take time to review for the final. We did the assessment last time, right? Were you all able to do the assessment? It's gonna be part of your grade. So we had the assessment, and then also, were you all able to start on the critical thinking component? Kind of, okay. So keep in mind, we're gonna make that due next Wednesday. You submitted on Moodle, right? So if you have any issues, let me know. But it's gonna be for a grade, for a quiz grade, okay? So you can team up, you can ask questions, you can email, do what you need to do to get it submitted on time. Those are the main things. Any questions about anything before we kind of get back into it? Okay, so if there aren't questions, I am going to proceed. I kind of do want to walk around, just a little bit, and I think this is going to be okay. Ooh, okay, we're gonna do this. Let's see if this works. So we are in full blast today. Let's go Bluetooth. The keyboard is connected. this one. Okay. Let's see. So I'm kind of tethered, but that's okay. Okay. So I think this will work. So this is we're continuing chapter 4 with inverse, exponential, and log functions. So today we want to take a look at exponential functions. Do you mind clearing that for me, somebody? The board.
I think he wants to keep that.
Yeah, he said it's okay. Did he? If you could take a picture of it, I don't know. It'll be okay. He'll know it. Just go ahead and clear it. It'll be okay. Are you taking a picture? Do I have a white space? No white space. Anyway, okay. Okay, so we're going to move into section 4.2, exponential functions. If you want to just stop there, you can. It's okay. Okay. So let's look at exponentials. So let me see. We'll call the definition of a to the power of m over n. So if we have a rational exponent, if a is a real number, m is an integer, n is a positive integer, then again, when we have a fraction in the exponent, the denominator of that fraction is the index of the radical. I don't have my normal one, so I can do this. So again, the denominator of the exponent, is the index of the radical, right? That's clear. Okay, let's keep going. Okay, I'm going to let that be. So for example, if we have 16 to the power of 3 over 4, we can rewrite it as the 4th root of 16 quantity cubed. What to the power of 4 gives us 16? 2, right? Because 2 times 2 times 2 times 2 is 16. So then the 4th root of 16 is going to be 2, and then 2 to the power of 3 is 8. Let's keep it going. What does a negative exponent mean? It goes where? To the denominator, right? So 27 to the power of 1 over 3 means what? Cube what? Cube root of 27. So cube root of 27 is 3. So I think this is okay. Any questions here before we go forward? So again, the denominator of our exponent is the index of the radical. Okay, go ahead.
Would it be wrong to do the 3 with something inside?
So, okay, let me think about it. There is, that's coming up. It's not wrong, but there is something that we have to kind of consider. Let me think about it. Just trying to think of how to articulate it. So you see how we have the 4th root of 16 cubed? If we did 16 cubed, it's something where one of them forces or causes an absolute value. Like if we square it first, right, then it forces it to be positive, so it forces the result to be an absolute value. Well, that's going to come up, and we'll talk about it whenever it arises in the notes. But that's the only thing that's different. But otherwise, what you said is okay. It's fine. Let me see. In this section, we're going to extend the definition of a to the power of r to include all real numbers, not just rational values of the exponent. For example, we're going to say 2 to the power of root 3 might be evaluated by approximating the exponent root 3 with those rational numbers. So square root of 3 is an irrational, but we can approximate that radical or that exponential by using those decimals, right? So that'll give us approximation. So we could say like 2 to the power of 1.7. And then we say 2 to the power of 1.73. So these are like the decimals. We're truncating the decimals of the square root of 3, and that would just give us an approximation for this exponential. We're probably not going to be doing too much of stuff like that. We usually kind of work it a little bit differently. Let's see. So because these values approach the value of root 3, it seems more reasonable that 2 times the square root of 3 should be approximated more and more closely by these numbers. Okay. So yeah, I'm going to let that be. Yeah, we just kind of have that. To show that this assumption is reasonable, see the graphs of the function f of x equals 2 to the power of x with 3 different domains. Integer. Okay, so the one on the far left, we're saying the integers are the domain, right? So if we do the integers, right, when x is negative 2, we get 1 over 4, and then we get 1 over 2, and then we get 1. So we're just plotting those points that you see on the left, right? So if we plot the x values corresponding to the integers, we'll get a graph like that. And then it says, for the middle one, it says selected rational numbers is the domain. So just a select number of fractions, and we get something like this. So then the real number system, we get this graph. What you see on the far right is the general form of our exponential. So that's the general shape of an exponential that we're going to be working with, right? So that's the general shape of an exponential. Okay. I want to make you aware that we are recording this session, just the audio. So just kind of be aware of that. Exponents and properties. Using the interpretation of real exponents, all rules and theorems for exponents are valid for all real numbers, not just rational ones. Let me see. I'm going to let this be for now. So we have the traditional properties of exponents. Let's see. A to the power of x is a unique real number for all real numbers x. A to the power of b is equal to a to the c if and only if the exponents are equal. All right, so that part B says, a to the b equals a to the c if and only if the exponents are equal. We're going to use that to solve exponential equations. If a is positive and m is less than n, then a to the m is going to be less than a to the n. If a is between 0 and 1 and m is less than n, then the reverse is the case. Right? We're going to explore all of these. I know it's a little bit harder to see it when we generalize in that sense. I think when we start working examples, it'll clear up. Any questions before we go forward? Again, I feel like once we work a few examples, this stuff will start to click, and it's not as bad as it looks. I'm going to let this be too. I really want to get to an example. I'm going to let that be. Okay, let's work this. So it says, if f of x equals 2 to the x, find each of the following, f of negative 1. So if we're doing f of negative 1, what's going to happen here? 2 to the power of negative 1. What does that mean? When we have a negative exponent, it goes to the denominator. So then what's the solution there? Is that okay with everyone? Does that make sense? Stop me if it doesn't. Blink your eyes. Blink your eyes if you need assistance. So a negative exponent, right? Let's look at it. A negative exponent means it forces it down. So it's going to, instead of being 2 to the negative 1, it's going to be 1 over 2 to the 1. But then 2 to the 1 is just 2. Is that okay? Let's try another one. But a negative exponent forces that part to the bottom, to the denominator. Let's just try another one.
Which makes it positive?
That's how you're going to write the exponent as a positive by moving it to the denominator. So, for instance, if x is 3, 2 to the power of 3, what does that mean?
2 times 2 times 2.
So that's going to be 8, right? This is all correct, right? So 2 to the power of 3 means 2 times 2 times 2, which is just 8 here. All right, let's try this one. So if we have 2 to the power of 5 halves, what is that 2? If we say 2 to the power of 5 over 2, what does that denominator of 2 mean? Square root, right? So we're taking the square root of 2, and then that result to the power of what? 5. So like Miss Bomick, right, was saying that we should be able to move that 5 into the radical. It could be on the outside, but in this case, I'll more so move it to the inside. Then now if we're doing the square root of 32, right, do we have any perfect squares in there?
4.
Yeah, 16, right? Because 32 is what times what? So let's write this one out. Let's write, no. Whew, life flashed before my eyes. Let's go like this, like that. Let's write this one out. Let's go this color, that's fine. Okay. Is that what I clicked it? Anyway. How do I? Okay. Thank you. So if we're doing f of 5 over 2, what we're doing is 2 to the power of 5 over 2, right? We said that denominator in the exponent means square root. So this is actually okay. Square root of 2, quantity to the power of 5. This is actually okay. And we can rewrite it. It should be the same. This is going to be the same as the square root of 2 to the power of 5. I want to say if that power of 5 were even, that's what will force the absolute value. Because when we square a positive, it forces it to a positive. If we square a negative, it forces it to a positive. So instead of it being like 5.
Is that why it was just 2? Or just 1?
No. We haven't gotten to that. But that's coming up. That's coming up. So, but for here, so the 2 is the index of the radical, so that's why it was square root. And then the 5 is remaining, so we can actually move that 5 into the radical. So then what's 2 to the power of 5? 2 times 2 times 2 times 2 times 2. What is that? 64. Okay, what's 2 times 2?
4.
Times 2? Times 2? Times 2. 32, right? So this is the square root of 32. But now we need to simplify, we need to reduce that down or simplify that, right? So we need to take out all our perfect squares. What's the largest perfect square that we have inside of 32? 16, right? Because 32 is what times what? 16 times. So this is the same as the square root of 16 times 2. We can break this apart because these are positive real numbers. We can do the following. Square root of 16 times the square root of 2. What's the square root of 16? 4, and then square root of 2 just persists. I think that's it. Okay, let's see how do we do. I just want to see the answer first. 4 times the square root. Actually, we can leave that. That actually fit. Wow. Okay. Go ahead. Go ahead.
How did you go from? You probably explained that already, but maybe I'm just looking at it. How did you get from this to this?
Okay. So let's do. Oh no.
That's what I'm saying.
All right. So let's do this. Come on. We'll do blue. So if we have 2 to the power of 5 over 2, is it safe to say that this is the same as 2 to the power of 5 times 1/2?
Yeah.
Is that okay? Right? Right? Because 5 times 1/2 is 5 over 2, right? So then if we say a power times another power, that's the same as doing what? A power to what? So this, I don't know how to get you to see it backwards, but if we have 2 to the power of 5 times 1/2, this is the same as 2 to the power of 5 to the power of 1/2. If we say a power to another power, we multiply those numbers. The goal is to get it into this form. Right? So then once we separate it like that, then we can take the square root of that 2 to the 5th, and then we can kind of move forward. So yeah, let's work a few more examples, and it should start to click, right? Okay, let's try another one. Actually, I kind of want to get rid of that now. I don't want to clear. It'd be nice if I could move that, but let's just go like this. Okay. So I'll let that persist. You're not going to work? Okay. Okay, so if f of x equals this, find the following. Something like this, I would just use the calculator. All right? If we're doing f of, and let's do it like, let's clear the ink. So if we said f of 4.92, we would just say 2 to the power of 4.92. I would just use the calculator. All right. Again, use a calculator. So that's you would just have to practice that on your own. I can do a quick demo here. Let me see if it'll show. Okay, that's looking good. Let's close these tabs and let's open this up. We get out at 11:26. Okay. I know, because I have my 2 classes. One ends at 11:26, one ends at 11:16. So it always, I can't, it's not consistent, so I always get stuck. Okay, let's clear this out. Okay, so let's just see this in action, right? So we can say 2 to the power of, open parentheses, 4.92, and we'll get that result. 30.2738, blah, 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 blah. Is that okay? Okay, we're gonna let that be. Okay, let's let that be. Okay, so so now what we mean by an exponential is going to be some, let me see, a is some positive real number, let me see. Yeah, a positive real number not equal to 1 to the power of some variable. So exponential, we're saying the variable is now in our exponent, right? So that's what we mean by an exponential. We actually saw the graph of this earlier. We don't allow 1 as the base for an exponential because if a were 1, if we said 1 to the power of x, 1 to the power of anything is what? Is 1, right? Right? So then it's no longer going to behave like an exponential. So the base can be any positive real number not equal to 1. I think that's okay. So we repeat the final graph. Let me see. So this is just kind of recapping. Again, this is just a general form of an exponential. It looks like the image that you see on the right side of the screen. Some key points. Okay, so some features of the exponential I want to mention really quickly. We have a horizontal asymptote. What's an asymptote? Yeah, it gets like, so the exponential does not cross the horizontal asymptote, right? It gets really close to it, but it doesn't cross it. So the horizontal asymptote in this case is going to be what? The x-axis, that guy right there, right? So it'll get close to that, but it won't cross it. Now, in a general sense, we can cross the horizontal asymptote. We can cross those, but this is describing what's happening in the long term. Vertical asymptotes, we don't cross. We typically don't cross those at all. But there are cases, not in the exponential, but there are cases where we will cross the horizontal. But what all the horizontal asymptote means in the long run, as we go off to negative infinity, our exponential is going to get really, really close. It's going to look like it's on the line, but if you zoom in, you'll actually find that there's actual space between our graph and that asymptote, right? That's what's going to happen there. Is there a vertical asymptote here going off to the right? For instance, if we look at this graph, can we get to when x is 10? Is this defined from when x is 10? Is there a vertical asymptote? So is it defined for x equal to 10? When x is 10, can we get a y value? Right? 2 to the power of 10, whatever that is. 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, right? There it is. There it is, 1024. I was like, I know we can do that number. So what's happening on the right-hand side, there's no vertical asymptote. So actually, every x going to the right is defined. But just like our bank accounts are about to do, it just grows very, very quickly, right? That actually reminds me, there's actually a story that I usually, and I'm killing time, but it's okay. There's a story I usually do when talking about exponentials. And I'm actually going to open this up to talk about it. Let's go here. Okay, so there's a story of the man who invented chess, right? So the chessboard is what I think it's a 8x8 square tile, right? And so you have a total of 64 tiles on the board. So and we're familiar with chess. You have the pawns and all the different pieces. So this inventor presented this game to the local ruler at the time, and the ruler was so pleased by this invention. He was like, "Oh, I really like this invention." He was like, "I'm going to offer you a reward of your weight in gold." So the ruler was going to offer a reward of the inventor's weight in gold, and the inventor said, "Well, I have a much better idea. Instead of paying me my weight in gold, what do you think about this proposal?" On the first tile, so let's see, let's do it like this. You know the story? So yeah, on the first tile, we're gonna put, I don't know, I need another one. I'll put G for grains of sand. We're gonna put 1 grain of wheat. We're gonna let that be for now. And then on the second tile, we're gonna double it and put 2 grains of wheat, right? And then on the third tile, we're gonna put 4, and then let's do a few more. On the fourth, it'll be 8, so on and so on. And so again, it's a total of 64 until we get to the 64th tile, right? So and so the ruler thought about it for a moment, and he said to himself, he was like, "Oh yeah, this is a much better deal than paying your weight in gold. I just pay you a few grains of wheat, we'll be good to go." So the ruler agreed. Let's see, what did the ruler agree to? How many grains of wheat did he actually agree to? Okay, so on the first tile, we had one grain of wheat. Just notice that this is the same as 2 to the power of 0. Let me see. Let me think about it. I think this one goes like this. This is going to be 2 to the n. And then I'm going to say total. Actually, let's not do it like that. Wait. Grains. Wait. So grains of wheat, we'll say grains there, and then we're going to say total wheat, right? Okay. So the total on the first tile, he just has 1 grain of wheat, right? I'm going to let that be for now. On the second tile, he does 2 grains. Notice that 2 is 2 to the power of 1, right? So now he has a total of 3 grains of wheat, which is going to be 2 squared minus 1. So this is 2 to the 1 minus 1, right? Let's keep going. Let's just keep going. On the third tile is 4 grains of wheat. Is this okay? This is, let me see, 0. This is 2 squared, right? And now the total is 4 plus 3, which is 7, which is 2 cubed minus 1. Is this okay? So we should be able to take it all the way to the nth degree. So when we get on the 64th tile, how many grains of wheat? We don't know how many grains of wheat are going to be there. So notice, on the third one, it was 2 squared. On the second one, it was 2 to the first. On the first one, it's 2 to the 0. What's going to be the result on the fourth tile? 2 to what power? 2, no, on the fourth tile. 2 to the what? Third, right? You see the 0, 1, 2, 3? And so then, what's the total? The total is what? 7 and 8 is, what's that? 15? Notice that 15 is 2 to the 4 minus 1. Is this okay? So when we get down to the 64th tile, the number of grains of wheat on that tile specifically is going to be what? 2 to the power of what? 60 what? Now look, 4 was 2 to the third. 3 was 2 squared. 63, right? So 64 is going to, on that tile, is going to be 2 to the power of 63 grains of wheat. The total number of tiles is going to be 2 to the power of 64 minus 1. If you crunch that number, it ends up being like something like, let's see, can we do this really quickly? Let me see if the calculator can handle it. Well, this is college algebra. College, emphasis on the college algebra, so we got to go a little bit deeper.
Oh my God, that's so big.
It's a huge number. I was about to do something completely inappropriate. I was going to say, that's what she said. I've been watching way too much The Office. So, like, what's his name? Michael, what's his name? Stephen Carell. They be in the weirdest situations. I be crying. Because like, they were fighting. He was like, Toby, I can't stand this. You're making it so difficult. And Steve was like, that's what she said. Like, you know, just so, you know. The race day?
Yeah, it was called Race Day. Oh, it was like on the first season.
Oh yeah. They put the things.
That was hilarious.
That's just Steve Carell is a fool on that show. He has me crying all the time. Come on, why are you not working? Let's reload and refresh. But yeah, that show has me crying. So like, yeah, come on. Why are you behaving like this? There it is. 2 to the power of, we're gonna say 64 minus 1. Let's see if it works. All right, let's see. So we got 10 to the power of 9. Let me write this out real quick. So we have a 1, 8, double 4, 6, 7, 4, 4, 0, 7, and there's probably more. Let me see, 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, let's see what number this is. There's 1,000 right there. Million, billion, trillion, quadrillion, quintillion. That's right. So the total, yeah, quintillion, right? Quintillion. So these are grains of wheat. So yeah, that's the conclusion of the story. So let's go back to the story. So let's see what happened here, right? So the ruler thought that he was getting a deal. He thought he was getting over on the ruler, and the ruler apparently outwitted him. This ends up being about 18 quintillion grains of wheat. So that amount of wheat doesn't exist in the world today. If that amount of wheat did exist, apparently it would fit just inside, I think it said 25 mile by 25 mile by 1,000 foot high silo, something like that. I think it was some kind of dimensions like that. I think it was 25 miles. Maybe that wasn't the right number, but it was some large number. I'd have to sit and think about where that would fit in, or check back to my sources. But again, the whole point was that was more wheat that existed ever, right? Like there was no way he was going to be able to pay him what he agreed to. So the part of the story that the book where I got this from doesn't mention. Now it might not be 25 miles. I got to think about what was those dimensions. I got to go back and look at that. But the part of the thing that was not in that story that I've heard was that when the ruler realized that he got duped, apparently he did off with his head. He like killed the ruler. I mean the inventor, because he was like, oh, you're not going to trick me. So he just killed him apparently. But he's the king, so the king could do whatever they want. Like that's the thing with the kings. It's crazy. It's not like a democracy.
It was a video.
Mm. Okay.
And he just couldn't pay him. It was like he was just trying to find other sources trying to pay him, and he was just like, no.
Yeah. So, but yeah, and so it's like, but yeah, so that was just an example on how quickly things can grow in an exponential sense. Nature typically does a little bit more of what we call a logistic function, where it'll start off as an exponential, like if you talk about like population growth or things of that nature. It'll start off growing exponentially, but then it'll kind of level out and kind of behave like a log. That's called the logistic function, and that's a little bit more of how nature typically goes, but again, our bank account's about to behave exponentially, grow exponentially like this. So we're going to get ready. Okay, so let's kind of keep it moving. I'm watching the clock. You said 26, right? Okay, let's keep it going. So again, the general graph of an exponential, we have 3 key points when x is -1, when x is 0, when x is 1. And that typically gives us a general sense of how the exponential is behaving. Okay, let's keep it going. Oh. Yeah, okay, so given a graph like this, what's the domain? How far left does this graph go? How far right does it go? It does go to positive infinity. Okay. What's the range? How far down does it go?
Not including 0.
But not including 0, right? So we get a parenthesis. So we get really, really close to 0, but we don't reach it. How far up does it go? Okay. I can't outsmart you all with that question anymore. What's going on here? We talked about the range. What's the difference between these two? Horizontal asymptote, we talked about that. Passes through those key points when x is -1, 0, and 1. So this is an example of exponential decay, all right? So instead of growing exponentially, now we're looking at something that's decaying exponentially. So we have like, you could talk, this pops up a lot in like when we talk about half-life. So like shelf life and like, okay, how long does it take for half of this material to decay? Especially when we get into like chemistry and things of that nature. Okay, we're gonna let that be. Still have a horizontal asymptotes, still those. Yeah, I'm gonna let this be too. This is kind of mentioning transformations. If the top right is the general exponential, if we replace x with -x, how does that affect the graph? If the negative goes inside our function, flips it over the y-axis. That's how we're getting the second image, right? So the second one is still an exponential, but now the exponent is now negative. So instead of exponential growth, we have exponential decay. Okay. I'm going to let that be. So this is still kind of discussing transformations. And like if we vary the base, right? If the blue, we have like f of x equals 2 to the power of x. What do we notice on the right-hand side as that base of the exponential gets larger and larger and larger? What's kind of happening to our exponential?
Coming closer to the...
Yeah, it's kind of, it's like a vertical stretch, right? So yeah, it's like a vertical stretch. It's becoming more and more narrow. What do we notice? What's happening on the left-hand side? Is that base getting bigger or is it getting smaller?
Bigger.
So like as we go from blue to red to green, is it getting bigger or smaller? Smaller, right? Right? The denominator is getting bigger. For a fraction, it's the reverse, right? But notice as that base gets smaller, it's becoming more steep. But that's because that's the reason that was behaving that way is because that base is between 0 and 1, right? So when the base is between 0 and 1, it's kind of reversed versus the base being larger than 1, then it kind of follows our intuition. So I wouldn't worry too much about that. Characteristics of the graph of an exponential, we have those key points when x is -1, 0, and 1. If the base is larger than 1, it's going to be an increasing function. If the base is between 0 and 1, it's going to be a decreasing function. The x-axis is a horizontal asymptote, and the domain is all reals. The range is 0 to infinity. So these are just properties of the exponential. These kind of come out naturally as we start working different examples. Okay, we're asked to give the domain and range. I'm trying to think. We didn't move it up and down. Yeah. What would be the domain of this? So in a general sense, what's the domain of an exponential? Okay, so it should be all reals. Did we move this graph up and down at all?
No.
So then what would be the range? It should be 0 to infinity, right? We could plot the graph, right? So if we were going to plot the graph, we would choose some x values, find the corresponding y's, and plot the points. We typically, again, we want to use those key points, -1, 0, 1. That really helps us out a lot to give us a sense of the direction. Would this one be exponential growth or exponential decay? Why are you saying growth? Okay. So I heard exponential growth because the x isn't negative. Well, watch this. So then what if we did 1 over, let's not use that color though. I feel like it's so dry. Let's use blue. Okay, what if so here's the original, right? 1 over 5 to the power of x, we're going to say f of x, right? Is it safe to say that this is the same as 5 to the power of negative x? Is that true?
Yeah, it is.
So if these are the same, would it be exponential growth or exponential decay? Is that okay? Okay, so is that okay, right? Because 1 over 5 is the same as 5 to the negative 1. Then negative 1 times x is negative x. So the reason this one is exponential decay is because that base is between 0 and 1. Or in other words, you saw how we transformed it into this form. We still have our negative exponent. It's going to be exponential decay. So on the far left, it's going to start high, and then it's going to come down and approach 0. So if we were to plot it, we would see it. It'll be something like this. So they chose the x values on the left. They just found the corresponding y values on the right. All right. Okay, so we chose the x values on the left, found the corresponding y's on the right, plotted the points. We get an image like this. Is it okay? Yeah, horizontal asymptote? No? Is that okay? Because we have 1 over 5 to the power of negative 2. Okay, so let's do this. So let's do when x is negative 2. All right? This is going to be what? F of negative 2 is 1 over 5 to the power of negative 2, right? What does a negative exponent mean? It goes to the bottom, right? Okay, that's fine. Yeah, you can say 1 over 5. When we say a fraction divided by a squared, right, still squared. If we say a fraction divided by another fraction, what happens? Keep change, flip, right? So this is actually the same as 1 over 25. So then 1 over 25, if we do keep change flip, just becomes 25. Right? So it's a few different dynamics going on there. I kind of want to try another one. But yeah, let's kind of move forward. Okay, let's see what else we got. Graph this. So let's try this one the same way they did the last one. Let's make a table really quickly. So we're going to choose some x values. So let's choose some x's, find the corresponding y's. Let's go what? Negative 4, negative 3, negative 2, negative 1, 0, 1, 2. Let's kind of clean it up a bit. Let's clear the ink. So we're going to choose x's, find the corresponding y's. Let's go negative 3, negative 2, negative 1, 0, 1, 2, 3. So notice I just chose those x values. Now let's find the corresponding y's. Ow. So when x is negative 3. Okay, now notice we have a negative 2 to the power of x. So let's do when x is negative 3. So we're going to say f of negative 3, that's going to be negative 2. Let me see something. Oh no. To the power of what? Negative 3. Now, what do we do first? We have negative 2 to the power of negative 3. What do we do first? Okay. So which do we handle first? Do we look at the negative first or the exponent first? Exponent because of what? Please. PEMDAS, right? Please excuse my dear Aunt Sally. There are no parentheses, but we do have an exponent. We have to decide between focusing on the exponent or doing the multiplication. We're going to do the exponent first. So then this is going to be the same as, now if we said 2 to the power of negative 3, what happens? 1 over 8, right? So 1 over 2 to the third, or it's going to be negative 1 over 8. Is that okay? I don't know how much more I could write there. Like, that's why I was like trying to talk you through it. It's not a dumb question. Let's look at it. So, I mean, only other thing I can think to do is say negative 1 over 2 to the third. Then it's going to be negative 1 over 8. So what's the next one going to be? Negative 1 over 4. Do we agree? What's the next one? Negative 1/2. When x is 0, 2 to the power of zeros. So what's the result here? Negative 1, right? When x is 1, let's do that one. So f of 1 is going to be a negative 2 to the power of 1. What's that answer? Negative 2, right? What about when x is 2? Because of the way it's written, right? F of 2 is going to be negative 2 squared. So because can somebody tell me why is it not positive 4? Because this right here. Because we don't have parentheses. If we had parentheses, then it would be negative 2 times negative 2 is positive 4. But because we don't have parentheses, I wish I could do an undo. Because we don't have parentheses, we're doing negative 2 squared. We do the exponent first, which is 2 times 2 is 4. And then 4 times negative 1 is negative 4. So then I think this one is negative 8, right? So let's do a quick sketch. Again, it's because there are no parentheses. This is why this is behaving this way. So if we did a quick sketch, x goes from negative 3 to 3. Y goes from pretty much 0 to like 10. So we can do, let's do a better graph though. Better window. Oh no, that's not a good window. Okay. And let's kind of go like this. I'm thinking something kind of like this, all right? So let me see, 1, 2, 3, 4 is enough. 1, 2, 3, 4. 1, 2, 3, 4. Here's our 0. And then if we're going down to like 10, let's go by 2s. 2. 2, 4, 6, 8, 10. Okay, and then 2 there, right? So if we were to plot these, when x is negative 3, negative 1/8, so it's really close to 0, so we're about there. Negative 2, negative 1/4, a little bit further away, but not by much. Negative 1, negative 1/2 is here. Notice we should have this thing going on. When x is 0, we're at negative 1, which is about here. 1, negative 2. Oh, over 2 down 4. Thank you. Over what, 3 down 8, so on and so on. So if we connect it with a smooth curve, we'll get something that behaves, I can't see, like that. Okay, but so now, how does this relate to the original graph of the exponential? Flipped over the x-axis, right? This one was flipped over the x-axis. So because the negative was outside our basic function. In the previous one, the negative was inside our basic function, so it flipped it horizontally. This one, the negative is outside our basic function, so it flips it vertically, right? So it flipped up to down, okay? I actually kind of want to clear. So you see they got the same graph we have. I'm going to, I don't know, I'm just clear the ink. I think that's a simple thing there. Okay, any questions here? Any questions here? We are recording, so I have proof. Okay, so now we're going to use transformations to graph this one, right? We have the base function of an exponential. It starts off kind of flat and then it grows exponentially. What's the transformation going on here? If we have that plus 3, is that inside our basic function or outside our basic function? It's inside. So is inside vertical or horizontal? Inside is horizontal. Does that follow our intuition or is that the reverse of our intuition? That is the reverse of our intuition. So how does that plus 3 affect our graph? It should go left 3 units, right? So we could follow the point 0, 1, and then it should just go left 3, and so then that'll be the final graph. So see the point 0, 1, if we go left 3, then we'll be at negative 3, 1, and the rest of it's all the same as far as the graph. Any questions here? Okay, so we use transformations there to graph this exponential. Okay, can someone tell me the transformation is going on here? Right 2, down 1 again. So we have our asymptote and we have the point 0, 1. We can use those to follow. If we go right 2, so that point 0, 1, we go right 2, we follow it. If we go down 1, the whole asymptote drops by 1, right? So we can follow those points. The horizontal asymptote. The x-axis, right? So if we drop by 1, now it's going to be at y equals -1. So yeah, we just use transformations there. I hope this is recording. Okay, solve. I'm just going to kind of do this one. I don't know how to. When you see something like this, what's the first thing that comes to your mind? Do you notice? Did you see anything today that we mentioned on how to solve exponential equations? Okay. So can we get these two expressions to have the same base? What base do you think we're trying to get them both to be? 3, right? Can we get them both to a base of 3? How do we rewrite the one on the left to have 3 to the power of -1, or -1 times x is going to be, so the left is going to become 3 to the power of -x. Is that okay? Because we did this one earlier, right? All right. Can we write the 81 with the base of 3? What times what is 81? 9 and 9, right? But then 9 is what? 3 times 3. So 81 is 3 to the power of. Okay, so 81 is 9 times 9, right? So, but 9 is 3 squared times another 3 squared. So when we multiply exponents of the same base, what do we do with those exponents? We add the exponents, right? So this is the same as 3 to the power of 4, right? So if we have 3 to the -x equals 3 to the 4, we said earlier that these two exponentials are equal if the exponents are equal. So all we do at this point, we say -x equals 4, and then 4 should equal -4. X equals -4. So again, the exponentials are equal if their exponents are equal. So on that second to last line where we have the 3 to the -x equals 3 to the 4, we just equate the exponents. Yeah, because they have the same base, right? Those two bases are equal, or those two expressions are equal if the exponents are equal, right? So we just said the -x equals 4, then x equals -4, right? So how do we know if this is correct? So if we say that x is -4, what should happen if we plug it into the original? We should get 81. Let's see. All right, so we're going to say parentheses 1/3 to the power of -4, close parentheses, and we get our 81. Okay, so this is one way that we have for solving exponential equations. Let me kind of clear this out. Yeah, because it's 1/3 times a third times a third times a third. So then you multiply across the bottom. So 3 to the power of 4, yeah. Okay, so a power to another power is going to be the product of the powers. Okay, I think they did the exact same thing that we did. I'm going to let that be. Okay, so say we wanted to solve something like this. What did we do in the last one to solve that equation? We got them to the same what? Base. What base do you think we're going to get them both here? 2 here. So we're going to get them both to 2. 2 to the power of x plus 4. What about 8? 8 is what? 8 is the same as 2 to the power of 3. We're going to say to the power of x minus 6. If we say a power to a power, if we say a power to a power, what do we do with those powers? We multiply, right? So this should be the same as 2 to the power of x plus 4 equals 2 to the power of 3 times this. 18, is that okay? So then what should be the case at this point? Set them equal, so then what? We can go ahead and distribute. We get our 3x minus 18. Then what? Subtract the x, we get what? 2x. If we so we got to add the 18. We get what? 22. I switched things around. So I did subtract x and I added 18. I just switched it in the order that's comfortable for me. So then x equals what? Look at God. Okay. So if this is correct, what should be the case? If we plug it into the original, it should be equal. Let's just do this one by hand. So we're going to do a quick check. So we're saying that 2 to the power of 11 plus 4 should be equal. The question is that equal to 8 to the power of 11 minus 6? What is that, 15? We're not going to be able to crunch that number. So let's do this instead. We're going to say 2 to the power of x plus 4. We're going to say minus 8 to the power of... You know what? I think we can do this by hand. Let me do this. I'm going to do this real quick. So say we wanted to do this by hand. What is that? 15, right? 2 to the power of 15. What's 11 minus 6? 5. So this is 8 to the power of 5. But 8 is what? Oh, no. 8 is what? 2 to the power of 3 to the power of 5, right? So then 2 to the 15 equals 2 to the 15, and we're good to go. That's all that we needed. We didn't really need the number. We just wanted to make sure that the left was equal to the right. Is this okay? Okay, I'm going to let that be. Watching the clock. So we might just do this one section today, which is fine. Okay, I'm going to clear the ink. Any questions before I get rid of this? Go ahead. That's coming up. Yeah, we're definitely going to do that one. Let's not jump to conclusions.
Well, okay, last year.
Let's not jump to conclusions. Let's say it was easy once we get out of the course. Once we move on, then we can make those statements. But right now, I don't know how it's gonna go. Okay, so I think we did all this stuff. We got that result, and we checked it. Okay.
I have a quiz on log next.
Today?
Yeah.
Yeah, that's coming up. We're definitely gonna be doing it. Okay. What about this one? What do you think? What have we been doing so far? Get them to the same base. So we might not be able to get these to the same base, but maybe we can use a similar technique, right? So 81 is what to what power? 9 squared. Can we go a little further? 3 to the 4, right? We could probably use the 9 squared. So let's see. So then it should be the case that, I don't like the way I'm going. Okay. If we have, riddle me this. If we had, let's do it like this. If we had x squared equals 9, how would you solve that? Okay, if we had x to the half, nope, no, okay, yeah. Okay, let's back up here. No. Hang tight. If we had the square root of x equals, 4, how would you solve this one? We would square both sides, all right? So we would say square it like that, right? If we had x to the half equals 4, how would you solve that one? What does x to the half mean? What does x to the half mean? What does x to the half mean? Okay, so the x to the half means we're taking the square root. So how do we cancel the square root? Yeah, we essentially do the same thing. That's why I did that. I just wanted to so we do the same thing. So to get rid of that half, we would say both to the power of 2. Does that make sense? Because now we're going to multiply those exponents, they cancel, right? So if we had x to the power of a third, I don't know, I'm just throwing a number out there. How did we get rid of that third? Not cube root, but power of 3, right? Both sides to the power of 3. Right? Is that okay? Same for the same reasons as before. Okay. So now let's come back to ours. So if we have this x to the power of 4 over 3 equals 81. Okay, let's do this. So let's rewrite it. This is the same as x to the power of 4 to the power of a third equals 81. How do we get rid of that third? Yeah, both sides to the power of 3, right? So this to the power of 3, this to the power of 3. We're just going to let that be for now. Okay, so that's going to cancel that out. Then we'll get this, what? X to the 4 equals this. I'm just going to leave that number. How do we get rid of the 4? Yes, the what? Fourth root, right? So we do fourth root here, fourth root here. Those are going to cancel. What can you tell me? It does need to kind of, I think we need an absolute value here, but I'm going to let that be for now. Now we have that fourth root of 81 to the power of 3. How can we rewrite that? 81 to the power of what? What is the index of 4? How do we write that as a rational exponent? A fourth, right? So we're saying to the power of 4. Long story short, this is the same as 81 to the power of 3 over 4. All right? So notice, when we started, we had x to the power of 4 over 3. I was just trying to lead you to this. So then to cancel it, just to the power of the reciprocal, right? So we could have just jumped straight to the power. I was in a class last night, and like somehow when we opened up the class, they were like, what if you taught class like it was church?
Oh my God.
You know, it's like, and we raised it to the power of 3 over 4. That would be a good time. That just sounds so funny to me. And when we do the one side of the equation, we do to the what?
No.
We do to the what? Okay. Go ahead. Just gotta laugh. When you say like if we have x to the power of a fraction, we can say both sides to the power of the reciprocal, because what happens, they're gonna cancel. So it's gonna, when we multiply them, it's gonna become 1 varies in, like, right?
That's the rule.
Right? Okay. So now let's kind of take it a little further. We can actually do the following. So we actually kind of had something a little bit earlier I liked, but we're going to pick it up here. So this is the same as the fourth root of 81, and then whatever the answer is to the power of 3. What's the fourth root of 81? 3, right? Because 3 times 3 times 3 times 3 is 81. So then this is really just 3 cubed, which is 27, right? Let me show you this. So we're going to go back here. Awesome sauce, you are working. I'm very proud of you. Okay. You got to talk to your technology, you know, because the technology is a reflection of our natural ability. So when people say, oh, you stupid, whatever, I'm like, dude, it's only doing what you tell it to do, you know. So anyway, but you got to talk nice to your technology if you want it to behave properly. So off the rip, we could have just said 8 to the power of 3 over 81. So let's do this 81 to the power of 3 over 4. And what answer should we get? 27.
Yeah.
All right, so we could have just gone straight there from the beginning. But again, it's not obvious off the rip, but once you kind of do this a few times, you start to discover the shortcut. And so, yeah.
So that's always true.
Let's not go, I mean, if you have the variable by itself, that's okay, but there's so many little nuances that can happen. You know, if you have the x to some rational exponent by itself, you can do this, but this is not always the best way to go, right? But you can do this. Like, I'm not going to take that away from you, but you just want to kind of be open to some different techniques, right? Because it's not always going to display like this. Get ready for a PJ. You know what I mean by a PJ? Poor joke. Okay. Did you hear about the Zen master that went to the baseball game? You know, when he ordered a hot dog, when the hot dog man was coming around? This is the joke.
No.
The Zen master that went to the baseball game, you know what? When he ordered a hot dog, what he ordered? One with everything. Okay. All right.
One with everything.
So, because Zen masters are supposedly one with everything. So when he went to the baseball game, he ordered a hot dog. He was like, "How do you want your hot dog?" He said, "One with everything." Anyway, okay.
What kind of hot dog is that?
Plus or minus. Cube root, hang tight, hang tight, hang tight. Do we need the plus? Take the fourth root. Yes. Okay, so we did miss something. Let's see. So because we did the fourth root, right? When we did that fourth root, whenever we do an even root, we're supposed to do plus or minus. I definitely forgot about that. Right? And then if we cube both sides, I think it's going to be plus or minus. Come on. Plus or minus 27. So yeah, I definitely forgot that. When we do an even root, like we did that fourth root, we got to do plus or minus. It's the same reasons for the square root that we discussed before. Is that okay? Okay, so I definitely forgot that. Whenever we do an even root, so like square root, fourth root, sixth root, we got to include the plus or minus.
Oh, so it's just
So Miss Bliss, hang tight. Go ahead.
I said just 27 would have been wrong.
It's supposed to be plus or minus 27. Yeah, 27 was only half of it. Yeah, so yeah. Whenever we do an even root, we got to do plus or minus. What's the time? Oh, it's 11:11. Very zen-like. It's 4 ones. Anyway.
Wait, that is one with everything.
Yeah, it's like, yeah. Look, it's very interesting. Okay, let me see. How many more slides? We are dragging today, but that's okay. We're having a good time. So we checked the plus or minus 27. So we definitely missed that one, but that's okay. Didn't we just do this one? Oh, an alternate method. There may be more than one way to solve the exponential equation. I think this is going to do the way we just did. But again, the main thing is that we need to do that for the plus or minus is what we missed. So they essentially did the same thing that we did, but we just missed the plus or minus. Okay, interest. So compound interest. I kind of want to talk about this, but since we're kind of pressed for time, I won't go deep in it. So compound interest, what it is, compound interest, we're going to introduce this concept of compound interest, starting with the lowest form of interest that we have, which is called simple interest. At the top of the screen, you see I equals PRT. That's the formula for simple interest. Where P is going to be the principal, which is the amount deposited into an account. R is the annual interest rate, expressed as a decimal, and T is the time in years. So if we have this account, say we have an account where we're going to deposit $1,000. Then we want to see what's going to be the balance at the end of the year. So that's where this P is going to be the $1,000 plus the interest earned on that account after 1 year. So that's going to be the principal times the rate. So then you see, that's where that first line that you see, the P times P plus R. Is that okay? We took the $1,000 plus the interest earned, right? So the 1,000 is the P, the interest earned is the PRT, but the T is 1 year, right? So then we get this part you see in blue, which is P times 1 plus R. So that's the balance at the end of the first year. So then say we take that, and at the end of the second year, we want to see the interest earned on that account, on that principal. So now the blue is the starting amount plus the interest earned on the blue. So we got to take the blue again times R. And then we get the second blue that you see, the P times 1 plus R squared. If you think about it, it'll make sense, right? So then we can keep going with that for year after year. So the third year is going to look something like this. P times 1 plus R cubed. What are we noticing about this equation? The first one was P times 1 plus R. After the year 2 was P times 1 plus R squared. After year 3 it was P times 1 plus R cubed. Each year, this one is what's happening. The exponent is... So whatever year we're at, the exponent is going to be that year, right? So this is using simple interest. Note, this is one compounding per year with the interest applied once in a year. So continuing this way produces a formula for our initial formula for compound interest. So we have this A equals P times 1 plus R to the power of T. This is with one compounding per year. So what we mean is, when we say compounding, that means how many times we apply the interest in a year. So if we apply the interest once per year, it looks like this. If we apply the interest multiple times per year, let me see if it's this one. So if we apply interest multiple times per year, the only change that we introduce is the n. So the rate gets divided by n, and the exponent gets multiplied by n. So this is called the compound interest formula, where A is going to be the future balance, P is the starting amount in the account of the principal, R is the rate expressed as the decimal, N are the number of compoundings per year, and T are the number of years. Is that okay? So this is the compound interest formula. You really just need to know how to use this. I don't mind you using the formula in class. We just need to know how to use it. I'm watching the clock. I see we're almost out of time. Let's at least do one of these. Suppose we have $1,000 deposited into an account paying 4% interest per year, compounded quarterly. Okay. Find the amount of the account after 10 years with no withdrawals. Okay. So we want the future amount after 10 years. So what's the principal? What are we starting? So here, let's write the formula first. Let's write the formula. Okay. And okay, so we're going to be using A of t is going to be P times 1 plus R over N to the power of NT. So then if we apply hours here, what's our principal? What are we depositing into the account? $1,000. All right. What is the rate? What's 4% expressed as a decimal? 0.04. Okay. What's our time? How many years? Sorry. 10 years, right? And then what's our N? How many compoundings per year? Right. So every 3 months? So we're going to apply the interest 4 times in that year. So now they gave us everything. Let's just plug it in to find the future amount. So the future balance after 10 years without withdrawals is going to be the $1,000 times 1 plus the rate, which is, again, we always express the rate as a decimal. Compounding is 4 to the power of 4 times 10 years. So we can actually just put that in our calculator. No, we would use a calculator here. Yeah, we would use a calculator. What's on your shirt? Is that what's it, Ursula? Yeah. Oh, that's Ursula. Okay. She used to, I think when I saw that movie when I was a kid, she creeped me out. Like she was one of the creepiest. Like I just always got this weird vibe from her. I was like, I don't like her. That was
The villain from Aladdin was creepier.
the new one or the old one? Jafar?
Yeah, Jafar.
I like the scar that was in the live Lion King.
I didn't get to see it.
Oh, you should definitely watch it.
Everybody was just like, don't. And then I was like,
No, yeah.
I feel like they made it too real. Unless somebody was like, people was act like a lot of people was just like, how did they get animals to act? And I was like, it's
CGI. Like, how do you not automatically think CGI in this day and age?
They said that like the animal's face expression. Like, I feel like it should have just been a little bit.
Yeah, it was a
more animated. Monotone.
It was, yeah, that's how I felt. I felt like it was missing a punch. When I went and watched it the second time, though, it was better when I watched it the second time. But that first time, I felt like it was missing something. But I did like the live action Aladdin. Like, I think Will Smith did a great job. Like, I think he actually said something that was real deep. Like, when he first got out of the cave and he was like, oh, what's your wish? He was like, make me a prince. He was like, now, there's some levels to this. Because I could just make you a prince. And you can be spending eternity with that guy. And it's like, hey, you guys see my castle? But he was like, no, when you're asking for a wish, you got to be specific. You know, I was like, I think he's actually talking about real manifestation. I was like, yo, this is deep. I'm liking this. But that movie was fun. I felt like it had just the right punch, just the right kick, just the right changes. Like Aladdin, I had a good time with that one. Oh, that was a good one. Like I liked that one. It was fun. The students were telling me that, let me see, 86, right? 1488. Apparently, Spider-Man was like bought out, or they had some kind of disagreement. And it's no longer, that's you all that said that? It's no longer part of Marvel?
Yeah.
I was like,
They couldn't come to an agreement.
I was like, is this for real?
They couldn't come to an agreement on the profit.
So I have a lot of conversations, and my conversations definitely run together. So I definitely be forgetting. Like, it's like,
Sony's still gonna make movies. It's just like Sony messed up the other Spider-Man.
Yeah, I did not like Toby. I like this latest installment. The latest guy's good.
Well, not Tom Holland. Yeah, but he's not gonna make
Yeah.
you like Tony's his mentor. Like how? Like
Okay, so let me see. How do we do? Do we have the result? I know. Yeah. So we got this result. Okay. Any questions here? Can I just go to the next one without advancing the slide? How do I? Okay, keep in mind the audio is still picking this up. Okay. I really want to leave this. Thank you. Yeah, it's okay. So we're gonna let this be. We need to wrap up because we're just about out of time. I'm gonna do a quick glance forward just to see if there's anything pertinent that we need to talk about. So you can, the rest I'm going to have to leave as an example, as an exercise, okay? So you can definitely handle that. This one takes a little bit of practice. You definitely want to look at this and give this a go and see if you can generate that number.
Are those numbers really? Because it is up to them.
The video or the slides are already on Moodle. I'll get the video up as soon as I can. Like, I tried to go live, but it won't connect. I think I need to install a VPN. So it should be recording. Hopefully, we'll have to check it in a moment. I'm going to have to leave this as an exercise. Just trying to see if there's anything different that we need to talk about. Oh, continuous compounding. Let's mention this really quickly. I'm watching the clock. So continuous compounding. Okay. So say we took our compounding. Say we had one compounding per year. What is this? So let's go back. Suppose the dollar is invested at 100%. So the rate, so the R is a 1. Compounding n times per year. Then the interest in decimal form is going to be a 1. And the interest rate pay period is going to be 1 per n, right? Where we're starting with $1. So the compounding at the end of year 1 is going to be the following. So if we did one compounding, it looks like the result is 2. And then if n is 2, it goes to 2.25, so on and so on. As n goes to 1,000,000, we're approaching some decimal. So as the number of compoundings go off to infinity, the resulting amount with that initial setup is approaching this decimal. This 2.7182, so on and so on, is going to be this term called E. So what this is, we take the limit as n goes to infinity, and this term approaches the number called E, and which is this irrational here. You don't have to worry about that. But then what happens is our formula basically becomes this. The future. So say we have continuous compoundings. So when we introduced it, we first introduced it where we had one compounding per year. Then we looked at multiple compoundings per year. Now suppose the interest was applied continuously. So it's just steadily growing. Then the limit as n goes to infinity, we get this. This is called the continuous compound interest formula. This is going to be, A is going to be the future amount, is going to be the principal times E is a function in the calculator. Again, E is this decimal here, it's just a function in the calculator. E to the power of R times T, all right? So this is called the continuous compounding interest formula, or continuous compound interest formula. I remember as A equals PERT. Give me just a moment because we're almost out of time. I'm trying to wrap up. So it says, notice with this one, it says the interest is compounded continuously. So we will use PERT, A equals PERT, plug in the components, and then you'd have to use your calculator here to finish it out. So then this one, okay, really quickly, if the investment was compounded annually, what would be our N?
What would be our what?
What would be N if we did the compoundings annually? Okay, let's skip that one. If it's semi-annually, how many compoundings per year is that? 2. If it's monthly, how many compoundings? 12. If it's daily, how many compoundings per year? 365. 365. If it's annually, how many compoundings would that be? 1, right? So continuously, we would use PERT, right? We're not going to use a number there. Continuously, we would use a different formula. Okay, so I just wanted to kind of mention that. So I think these are all of them. Annually, N is 1. Semi-annually is 2. Quarterly is 4. Monthly is 12. Daily is 365. Hey, but I definitely agree with you with this 365 and a quarter. But here we're going to use 365 for daily. And then continuously, we're going to use PERT. This is PE to the RT. Okay, I'm going to have to leave that as an exercise for you all. We could talk about exponential growth. I'm going to have to leave this as an exercise. You can kind of look at it. If it doesn't make sense, let me know outside of class. I'm just trying to see if there's anything. You can actually, this is all using a TI-83 as well. We can use the 83 to generate these images, 83, 84 plus, these kind of things. Is that it? I think that's the last one. Okay. I was ignoring a hand. Is there a question before I kind of shut it down? Okay, so I'm going to go ahead and stop the recording. So with that, we will end the session here. And from one beautiful mind to another, enjoy the rest of your day. So let's stop.